Sorry. Really? Okay, because I'm not going to change. Okay, because there's no way.
Okay, let's get started. This is the end of week 13, and all we have is one lecture next Tuesday. That's all we have left after you make it through today. You can make it. Last day for late assignments that are already over 4 days old is on Tuesday, 5 days from today. Oh, I've got to write. If it's after that date, it's an additional 50% reduction after that date. So, here's the deal. I took a quick look as fast as I could, and I just wanted to see if I saw any zeros. And at quick count, I saw 5 zeros. So there's 5 zeros out there. You have until 5 days to get them in. I bet some of you are going to be surprised. Watch the reaction. Did you know you had a zero? See how surprised he is? See that? There's several other same situation. You don't even know you have a zero. Right, you got 5 days. Final exam. A week from today, 2 p.m. 5 days after that, on the 17th at 3 p.m.
3?
I looked and remember I guessed how much time was on the first part of the final? I can't remember what I said. How many minutes? 45 I did? I was wrong. 42. Oh my God. Can you believe it? Isn't it weird? It's weird, isn't it? What I do is I look at how many points there are, and I look at how many points there were in the past, how much time there is, and whatever percent of these points are to the past is that same percent of the people. That seems like a lot of work to figure out how much time. That didn't take long. All right, any questions about what's going on? You realize your last homework assignment, which I want to review real quick. This is your last homework assignment. You have these problems. I don't know how many there are there, but these will all take you just a few minutes. Nobody's handed in the homework assignment yet, and yet after Tuesday's lecture, you had all the information necessary to do this homework already, but no one's attacked it. But you have those problems, which will each take a few minutes, and then you have this spreadsheet. Is this the one right here? Don't forget with this spreadsheet, you're supposed to use the data analysis to get the information on a table, place the table anywhere down here. But when you do these 4 forecasts, it's all about using cell locations in the equation. Going to, N, whatever, N22 and N23 or whatever, wherever the cell locations are that you're going to use to do these forecasts. And then X is going to be 20, the next one's going to be 21, 22, and 23. You're doing 4 forecasts based though on the information from that data analysis table. This is all due Tuesday by 2 o'clock, and then you can go ahead and take a deep breath and say, oh my God, I'm no more homework in this class. This, by the way, I think is our 10th homework assignment. Does that sound right? Maybe 11th, right around there. We have our last in-class assignment at the end of class today. Oh my gosh. It's almost too easy. I'm embarrassed that I accidentally made it too easy. Any other questions? That's it? Let's get to it. Here we go. Goodness of fit. There's 3 subjects we're going to learn when it comes to goodness of fit, evaluating if our forecasting equation fits the data correctly. The 3 are going to be the standard error of the estimate, which is designated, if you're reading into the book or the PowerPoints, it's always an S with a small little e. Standard error of the estimate. And don't get it confused with this. This is an S with a little e with a square. That's the variance of the residual. It's basically the standard error of the estimate squared. Or, if you have the variance of the residual, square root it, now you have the standard error of the estimate. All right? The next one is called the coefficient of determination. It's designated as an R squared. Now, don't get confused. There's some formulas where R squares there, and some of you, I've seen in the past, could accidentally square it when really it's already squared. The R square, where am I at here with R squared? Oh, what's going on? I thought I had a formula for R squared. Let me look. Oh no, this is the formula to get R squared right there, not in it though. But when you go from the coefficient of determination to the third one, which is adjusted R squared, there is an equation to calculate this that has R squared in it, and you might accidentally think you need to square it, but it's already squared. So you're using the number from here into this formula to do what's called an adjusted. Here's the key to this perfect multiple choice question. The reason we take the coefficient of determination and make it into an adjusted coefficient of determination is when the forecasting model has different number of explanatory variables. All right, everybody hear that? A different number of explanatory variables. Let me make sure you understand that. I'm going to bring up this page right here. Let me go up here. See this equation right there where my pointer is? See those two equations, those two models? The models are saying y, which is your forecast, equals your intercept, b sub o, plus your slope, b sub 1, times x sub 1. Forget the e on the end. Then the next model happens to be the same equation. So my question for you is, do these have the same amount or different amounts of explanatory variables? You guys whisper. How many? How many explanatory variables do you see? No, the intercept's not a variable. But I see where you would get that from. There's a, yeah, but there are two different ones. How many explanatory variables are in each model? One on each one. So we could use standard error of the estimate. Hey, you guys. We could use standard error of the estimate for this, or we could use coefficient of determination. But if one of these had an extra explanatory variable, you've got to go to the adjusted coefficient of determination to determine which one's better. All right, now here's the key. Are you ready? If you decide to use standard error of the estimate, the lower the number, the better. The model that has the lower standard error of the estimate, the better. If you decide to use coefficient of determination, R squared, the higher the number, the better. The larger, higher the number, better. And if you decide that you need to use adjusted R squared because each model has a different number of explanatory variables, the higher the number, the better. Everybody hear that? That's the key to these. The reason that's the key, what I just told you how to analyze these, is because most of them is where you look at the output and basically just tell me which model's better. And it's a matter of you looking at the correct parts of the output to determine. I need to hear, your answer needs to include which numbers you're using to make that determination, which model's better. All right, let's get into this. You ready? Here's the first one, standard error of the estimate. Here's the formula in words up here. SSE stands for the sum squared error. You're about to see how that's calculated, SSE. Divided by, there it is, in variables, at n minus a k minus a 1. Here it is in words. Sample size is the n. Minus number of explanatory variables. I want to make sure you understand what that means. Let me go back to that output. We just talked about how many explanatory variables do each of these models have, Model 1 and Model 2. One explanatory variable. So in this case, this would be 1. It could be a 2, it could be a 3. We're not getting into models more than that though. Minus 1. Sample size minus the number of explanatory variables minus 1 divided into the sum squared error, which we'll learn how that's calculated. That's calculated based on this stuff over here, which we'll talk about. And then you square root the whole thing, and you found this. If you didn't square root it, what you just calculated was this, the variance of the residual. But once you square root it, now you found the standard error of the estimate, and you're doing this for each model, and whichever one has the lowest standard error of the estimate is the better fit. And that's the model you would select to use then to do your forecast. There's the equation. Now here's what SSE is. SSE is the sum of each one of these y's, so if I took 10, 6, and 5, what they actually ended up, are there in the data, but then took the equation, whatever our forecasting equation is, and did the same 3 forecasts. Then I compare, I take each one of those y's, I subtract the corresponding forecast, square each one of them, then I add it up. Now you're gonna see an example of this, so if I just said it too fast, don't worry about it. You're about to see an example of SSE actually being calculated. And that's what that numerator is, right there. Y minus the forecast of Y, squared. And then you add it up, the sum of. SSE stands for sum squared error. That's what the numerator is. Go ahead, Mom.
For a standard error of the estimate, is it the line underneath it? The SSR, where is that, what's that supposed to go? Underneath, right there.
Here, this goes with the coefficient determination. I put a line here to try to separate these two.
So SSR is just saying.
Yeah, that's, has nothing to do with this.
Is that Y forecast minus Y mean?
Yeah, that's this. That's SSR. And this is SST. That's SSR, that's SST instead of me just putting SST and SSR. Now here's what, well, hang on, we're
Would it be
jumping forward.
squared too, or just the Y minus Y mean?
Are we here?
Yeah, would it be the
This is
squared
the
part?
forecast of Y minus Y mean squared.
Squared.
And then add it all up, which we're about to do. We're about to do one of these with these numbers right here. Okay, so we now see how it's calculated, standard error of the estimate. I wonder if I should do one of these. Let me look in my notes. No, no. I want to look at this though. Here it is. This is a perfect question on the final exam. There will be an output there, and it will say, which model, Model 1 or Model 2, let me see if there's any, you'll probably be given some equations, so you could try to determine how many exploratory variables there are. Let's pretend though they have the same amount of exploratory variables. Maybe they both have 2, each model, or maybe they both have 1. So you look at this, and I need you to pick out the numbers and tell me why whatever model's better than the other. Now, you ready? I'm gonna pretend like I'm doing this question. I'm looking at these 2 models. I just read that they both have the same amount of exploratory variables. Maybe they both have 1, or maybe they both have 2, which is how many X's. And so I'm gonna go ahead and use the standard error. And I look at Model 1 and I see it's 63.26. I look at Model 2, it's 64.61. I'm rounding. And so I go ahead and say, Model 1 fits better. This is the model that should be used. You guys agree? Because it has the lower standard error. That's all there is to it. But you have to then recognize, what if there were multiple, what if the Model 1 had 1 explanatory variable, or 1 X, and Model 2 has 2 X's? Then you jump to the adjusted R squared, which means the adjusted coefficient of determination. That's what's used when the models have different number of explanatory variables. In that case, it says also to use Model 1, because the adjusted R squared 0.74 is larger than 0.73. So it's trying to tell you that Model 1 is a better fit. Here's the deal. In this particular example, the numbers are so close to each other that Model 1 is just barely a better fit. In most cases, the numbers are farther apart where one model sticks out better than the other as being a better fit. But in this case, they're pretty close. But whichever the case may be, whether there was some hits there, whether they have the same amount of explanatory variables, or if they have different amounts, the answer is going to be the same Model 1. But where the points are is where you showed me which number you used to make that determination. That's where the points are.
When do we use the adjusted R square, you said, if they're both equal?
No, you use the adjusted R squared if the 2 models have different number of explanatory variables, not the same, different. You would use either, standard error at this point if they have the same number of explanatory variables.
Oh, so in this one we would use the adjusted?
Well, we don't know. It doesn't say how, I don't think it tells us. As a matter of fact, it says the standard error of the estimate for Model 2 is greater than Model 1, 64.61 versus 63.26. Therefore, Model 1 provides a better fit for the sample data. So we use standard error, which probably means if this were a question on the exam, you would see equations that show you that they have the same number of explanatory variables, and you would know to use standard error then.
Are you gonna try and trick us?
I'm not gonna try to trick you. I don't think. Maybe, who knows? I doubt it.
We could also use, you said, the coefficient of determination.
We'll get into that. You can also use the coefficient of determination. Yes, Because look what would happen if you just used it on this one, what would happen? What would be the better model with coefficient of determination, anybody? Well, yeah, model 2 instead of model 1. No, is that right? Let me look, where is it? R squared? Yeah, 7527, 7526. They're almost the exact same number. Model 2, you have to go all the way to the 1,000th place. What is that? No, 10,000th place till you get a slightly higher number. So you almost want to go and use standard error just because those two numbers are so close to each other to see which model is better. But it does say model 2 is a hint better. Good one.
What's the, is it explained variance or explain?
Say that again?
Explain variance?
I can't hear you.
Is it explanatory variance?
This?
No, in the equation. Number of explanatory variance?
Hang on, almost a variables.
Variable?
Variables. So, for example, how many x's there are. Let me give you another example. Hang on, let me go to another one here. Hang on. Okay, here we go. Look at these two models. How many explanatory variables are there in model 1? No. How many x's? You're not even looking at the b's. How many x's? 1 x. There's 1 explanatory variable. Look at model 2. How many x's? 2 explanatory variables. That's that easy. Kind of, yeah, like that. It's not, or it will say model 1 has 1 explanatory variable, model 2 has 2 explanatory variables.
Is it always going to be
It
x?
can't be, it's just x. X's are the explanatory variables. X's are always the explanatory variables. Y's are always what we're forecasting. They're the reaction variable or whatever it's called. I can't even, you guys should know more. All right. So we can. Let's do this calculation right here, so we can see where this number comes from. This standard error of the estimate. Let's start right there and do the calculation. Let's go back to the thing right here, and it says SSE is y minus the forecast of y. But how do you get to the forecast of y? Yeah, I'm jumping too fast. Here we go. You ready? All right, here it is. Here's these numbers. What we're looking for, let me make sure I want to put this equation here. What we're looking for is SSE is equal to, and we're going to put it right here, which is y minus y forecast. Put a little hat here. And the whole thing squared, sum of. There it is. But the only way we can get these three forecasts is if we find the slope and the intercept. And then we have our regression equation with one explanatory variable, 1x. There's not two of them there. That would be multi-regression. So in order to do this, we got to go through the whole process to get the slope and the intercept, which we've done already. I want to refresh your memory. So to do so, right here, x minus the mean. Let's just do this real quick. The mean of x is 4. We take each x, subtract 4 to get x minus the mean of x. 6 minus 4, 2. 4 minus 4, 0. 2 minus 4, negative 2. There it is. Then the other half of this equation is y minus the mean of y, which is right here. The mean of y is 7. I'm taking each number minus 7. 10 minus 7, 3. 6 minus 7, negative 1. 5 minus 7, negative 2. Now, this column right here is where I take each one of these two numbers and multiply them by their corresponding numbers. 2 times 3 is 6. Negative 1 times 0 is 0. Negative 2 times negative 2 is 4. I add this column. 6 plus 4 is 10. This is where we get this number right there, which will allow us to find our slope. Okay, because look at the slope. The slope is E17 divided by D17. E17 is the sum of x minus the mean times y minus the mean. And the other one is x minus the mean squared right here. So we're going to take x minus the mean, which we've done right here, and square each one. 2 squared, 0 squared, 2 squared, add it up. our slope equals 10 divided by 8, which equals 1.25. There it is. Right there. I posted this, by the way. Our intercept, let's recall that equation. Don't forget, this is a subtraction equation, but it basically says you take the mean of y, so we're going to take 7, minus the slope you just calculated, 1.25, times the mean of x, which is 4. This is going to be your intercept, so we have 4 times 1.25, which is going to be 5, plus 7 makes, 7 minus 5, 2. Okay, here we go now. Where am I going to put this column? Put it right here. This is, and we're now going to do this right here. I can put it right here, actually. Right here. Y minus the forecast of y squared. Let's get our forecast. Here's our, we now have our intercept, we now have our slope. Our forecasting will be, here it is, forecast equals the intercept 2 plus the slope 1.25 times whatever x we tell it. Hang on, that's an x. I don't see an eraser. That's an x right there. So we have to get 3 forecasts so we can do this comparison. Here we go. Our first forecast, we're going to use a 6. Our second forecast, we'll use a 4. Our third forecast, we'll use a 2. Are you ready? 6 times 1.25, calculators, and then add 2. Tell me what you get. X equals 6. X equals 4. X equals 2. Here's my calculator. 1.25 times 6.
7.5.
7.5 plus 2 makes 9.5. Put a 4 in. 4 times 1.25 is 5. 5 plus 2 is 7. Is that correct? Equals 7. 2, put a 2 in. 2 times 1.25 is 2.5 plus 2 is 4.5. Is that right? Here we go now. I'm going to take, we got to take y, our actual, which is a 10, minus its corresponding forecast, which is 9.5, and then square it. 10 minus 9.5 is 0.5 squared, 0.25, right there. Do the second one. 6 is the actual, the forecast is 7, actual minus forecast is -1. Now square it, 1. Do the last one. 5 minus 4.5 is 0.5. Square it. 0.25. Add these up, you get 1.5. This is your SSE right there. Let me check the spreadsheet. Where's our SSE? Again, you gotta scroll down. There it is, right there. 0.25, 1.25, SSE added together is 1.5. There's our SSE. Where, let's go up here. Now that we have our SSE, watch how I'm doing this. You ready? Our SSE is 1.5. There's our numerator, divided by, what's our sample size here? How many are there? How many sets of variables do you have here? 3. So this is going to be 3 minus, how many explanatory variables do you have here? How many x's? 1. Stop. 1x. There's 1x. There's not another column of x's. Not another column of x's. So 1 minus 1. Now square root this whole thing. That's how you get the standard error of the estimate. Right there. You got to find that SSE divided by the sample size minus the number of explanatory variables minus 1. Oh yeah. Are you ready? There it is right there. The square root of I-24, which is our SSE, divided by 3 minus 1 minus 1 equals, here's our standard error of the estimate, 1.22. There it is, 1.22. This is how you get this number, right there. Now you would do this again for another explanatory variable. Like let's say there's another one here. If I'm asking you to do this on the exam, I'm asking you to only do it for one explanatory variable. I'm not gonna have you do it for a whole nother one, then to tell me which one's better. I may ask you just to calculate the SSE. I may ask you to only calculate the standard error of the estimate. I may ask you to only calculate the coefficient of determination or the advanced coefficient of determination. I may already be giving you some of this data and ask you to calculate it, where you don't have to do half of these calculations.
So the one that's lower is better?
The one that's lower is better. If you were looking at an output for just using the standard error, that whichever one's lower is better. Now, let's look at coefficient of determination. Here's the formula. SSR divided by SST, but I put it in words for you. SSR is the sum of each forecast minus the mean. And then you square it. Let me show you what I mean. Here's the forecast. Here they are right here. 9.5, 7, and 4.5. You gotta take each one of these. So this is gonna be Y hat, which is forecast, minus Y mean squared. This is the column we're doing right now. And this column is SSR. Y forecast, each forecast minus the mean squared, and then sum them up. Here we go. What's the mean of Y? Anybody? There it is. What is it? Anybody? You see it right here? 7. So I got to subtract 7 from each of these. 9.5 minus 7. Whoops. 2.5. 7 minus 7. 0. 4.5 minus 7. What is that? 2.5? Negative 2.5? Negative 2.5. Now, oh, I forgot to square them. 2.5 squared. I got to square each number. I know that one's 0. What's 2.5 squared? Anybody got a calculator? Not all at once. Oh, it disappears. Anybody got it?
6.2.
6.25, all right. 6.25, and then negative 2.5 squared is 6.25. You add this up, you get 12.5. Now let's look up our SSR on our spreadsheet. Here it is. We go up here. I gotta move it up. SSR, 6.5 plus 0 plus 6.5 equals 12.5. There's our SSR. So our numerator is 12.5 over SST. SST is each one of the Y's, 10, 6, and 5, minus the mean of Y squared. So right here, where is it? Y minus the mean of Y squared. Here's Y minus the mean. All we gotta do is square each of these numbers. 3 squared, 9, negative 1 squared, 1, negative 2 squared, 4, add them up, 9, 10, 14. Let's double check. Is SST 14? There it is right there by the pointer. This is 14. Do the math on this, 12.5 divided by 14, and our coefficient and determination is right there, 0.8929. I'm rounding to the 4th digit. 0.8929. Did everybody see how I got that number? Now, here comes the hardest part. I adjusted. I'm sorry, what? What is the variance of the residual? That's the standard error of the estimate, which is this formula right here. If it didn't have the square root, it would be the variance of the residual. But because we got a square root there, it now turned it into the standard error of the estimate. These two are the same number, like a variance and a standard deviation. A variance and a standard deviation. This is squared, and this is the square root of it. How do we know what's square and not square? If I'm asking for the standard error of the estimate, you've got to square root it. If I'm asking for the standard, the variance of the residual, same exact formula, but no square root. I don't know. Hey, don't forget, by the way, the last lecture of the semester on Tuesday will not be on the first half of the final. It will only be on the second half of the final. All right, so that way, what is that? It would make, so you don't have to worry about only having 2 days of that material to study. So everything from today backwards could be on this first half. The 42-minute part that you're taking on, what is it, a week from today? Yeah, a week from today? No, it's not. Oh yeah, today's Thursday? Oh, it is a week from today. I know it's Tuesday.
What's the y forecast minus y mean squared?
Right here?
Down there, yeah, that.
Right here.
Yeah.
So I took each one of these forecasts, 9.5, 7, 4.5, and subtracted the mean of 7.
But what does that, like, if we solve
Oh,
that?
and then I added up, and it's turned into SSR. So I'll put that right here. This is SSR. Don't forget, everything I'm doing on this board is on that spreadsheet, which is posted on Canvas. Everything I'm showing you right now is on this spreadsheet.
So, what's that 1 minus SS?
This right here?
Yeah.
This is an alternative calculation. Thank you for asking. For the coefficient of determination, it's usually SSR divided by SST, but it's also equal to 1 minus SSE divided by SST. Here's SSE, 1.5 divided by SST, which we have right here, 14. If you take that and put a 1 minus in front, do the division first, subtract from 1, you're going to get the exact same answer. Now, since he pointed that out, I want to make sure you realize something. There is a very obvious relationship between SST, SSR, and SSE. And you got to know that relationship when it comes to maybe using algebra to figure these out possibly. Everybody understand what I'm trying to tell you there? Those who are listening? Like you may be given 2 of those numbers, you should be able to logically figure out the third by knowing these formulas. For example, everybody with me? Look, if you got SSE here, SST here, you got SSR here, SST, between all of this, you should be able to figure them out by being given some of the information.
What numbers did you get 0.251 and 0.25?
Okay, this would be each y minus its forecast. So here's each y, 10 minus the forecast 9.5, 6 minus the forecast 7, and then 5 minus the forecast 4.5, but then I squared each one of those differences. So like 6 minus 9.5 would be 2.5. Oh, no, I'm sorry. 10 minus 9.5 is 0.5, but when you square it, it turns into 0.25. And then you add those up and you're at SSE, which is right here. Oops, where is it? Right here. Right there, those 3 right there. And it shows you which cells are being used and how they're being subtracted and squared. Now I want to point out something here. Here's where I'm confirming that SST equals, here's the equation, this is the key. This is one you should write down right now. SST equals SSR plus SSE. If I'm giving you any 2 of these, you can logically figure out the third with ease. My grandma could do the algebra on this. She's dead as a doornail. That's how easy this algebra is. 14 equals 12.5 plus 1.5. It's a good way to know if your SSR, your SSE, and your SST are correct or not. By knowing this formula.
What does SSR stand for?
Squared, hang on a minute, I try to remember. Squared sum of the residual. I think it's squared sum residual. That's it, squared sum residual.
Would we need to know that or no?
Not the name of it,
Okay.
but you need to know how to find it, how to calculate it,
Okay.
and where it fits.
So, are we doing that on the exam? All
Possibly.
of y minus?
Some of it, or maybe. You may not have to do all of it, maybe you only have to do part of it. Maybe you're already given the slope and the intercept. So that means 4 of these columns you don't even have to do then, if you already have that, right?
Yeah.
You get it?
Yeah.
You get it? I'm preparing you to understand that a lot of this, you can be given some of the information and get the other information without having to do all this work. This is what I want you to see here. And that's why this spreadsheet right here gives you in detail how to do each one, and then gives you this big hint. Now there's one more formula we have to do, we didn't do yet. Let me introduce you to it. Hang on a minute. Here's the coefficient of determination. The coefficient of determination is always between 0 and 1, and the closer to 1, or really the larger number, the better the fit. So when you're looking at coefficient of determination, and by the way, that's the same for the adjusted coefficient of determination. The larger the number, the closer to 1, because it'll always be point something like the correlation is point something between 0 and 1. The closer to 1, the larger the number, the better the fit. The better the fit. Now, go ahead.
Isn't all this stuff, you got the standard error of class?
Yeah.
So, like, what is that?
Once you have standard of the estimate, you now can compare one forecasting model to another. You would get the standard of the estimate of another model, and you compare the 2 of them, and you go, oh, this one's a better fit because it has a lower standard error of the estimate. This is the model I'm going to use now to do my forecast.
So these 3 variables is just for one?
These 3 what?
No, so like whatever you do right now is just for one.
Just for one. This is just for one model that happens to only have three variables, really, 3 sets of variables here. And there's a whole nother model, maybe it has 7 sets of variables possibly. Or maybe it has 2 different x's in a y. But here's what you need to get used to. Are you ready? Look at this. This is what you need to get used to right here. And I said, which model is a better model, knowing that each one of these models have the same number of explanatory variables? Okay, which model? Tell me what you're looking at this time.
Sample
Are
error.
you telling me?
Adjusted.
Based on standard error you're using, which model's better? Model 1. Based on the coefficient of determination, which model's better? Model 2, but very close, right? Instead, I said to you, hey, here's 2 different models, 1 and 2, but they have a different number of explanatory variables, each model does. Model 1 may have 1, Model 2 has 2. Which model's better? Now and tell me which numbers you use. Do I need to put it in the instructions and tell me which numbers you use? Because I'd hate for you guys just to go Model 1 without telling me which numbers you use. Why did you say Model 1? Because he went to the adjusted R-square and Model 1 happens to be larger, closer to 1. That's why Model 1's better based on the adjusted R-square. And he used adjusted R-square because I said there was different number of explanatory variables on each model. That's why he went ahead and used it.
So adjusted R squared is the same thing where like it has to be higher?
The higher the better. But don't forget, hang on. Lower the better on this one. Higher the better on these 2. Okay. Is coefficient of determination of what? They're not the exact same thing. This is an adjusted coefficient of determination. This is after adjusting, which I'm about to teach you how to do the adjustment. You ready? This is what's the last thing, which I kind of find it the hardest part, is now to turn your coefficient of determination into an adjusted coefficient of determination. So let's say in real life you had 2 models, and one had 2 explanatory variables and one has 1. You got to take both models all the way to the point of calculating the adjusted coefficient of determination so you can determine which model's better. And believe me, you're not going to do it manually like this. I'm showing you because you got to go through this because you're in college. Every software out there will give you these numbers just like this. But I want you to know where they're coming from and how really easy, they're not that hard to calculate. If you set up the columns like this, it's just picking the numbers out from the columns. You know, the different numbers. Oh, the sum of these is SSR. Oh, the sum of this is SSE. Where's SST? I lost it already. And the sum of the other one's SST. That's all there is to it. It's not that hard.
So for coefficient of determination, we're doing the same steps until we get to the equation?
You gotta do all the steps until you get to these 2 and then do the equation to get to the answer, yeah. Yeah, all the steps, unless you're given SSR already, or let's say you're given SSR and SSE, you may have to do math to find SST, then plug it in to find your coefficient of determination. You get it? It's not, you guys, it's not gonna be as hard as you think. As long as you can see the big picture and realize you may not be given all the information, you may be given part of this information, but you're gonna be given enough to quickly be able to find the numbers you need off of that.
You wouldn't be able to have it like where like the standard error is smaller and then also the adjusted R is smaller. It would have to be bigger, right?
In almost all cases, but it is possible. But you gotta remember, you wouldn't look at the adjusted unless the two models have a different number of explanatory variables. You don't use the adjusted unless they have different number of explanatory variables. You're gonna use one of the other two if they have the same number of explanatory variables.
For both the adjusted R squared and the coefficient, we have to do the higher numbers better.
Yes, everybody hear that? For both the coefficient determination and the adjusted coefficient, the winner is whichever one has the higher number, whichever model has the higher number of these two. In this case, if I said, hey, they have different number of explanatory variables, where's R squared? Right here, 0.7526, 0.7527, you're gonna go with the 27. It's a bigger number, only slightly, but it's a bigger number. You're gonna go with model 2. It's the right answer, even though we know if they have the same number of explanatory variables, model 1 wins. It has a lower here, and let's go here, it wins here too. Oh, wait, I'm sorry. Where's our, there. Oh, I blew it, didn't I? Sorry, let's do it again. I blew it. If the two models have different number of explanatory variables, you're gonna use the adjusted R squared, not R squared, and model 1 does have the higher number between these two, and it's significantly higher actually. So that's how you know model 1 would be better. But if it says it has the same number of explanatory variables, you would probably shoot to standard error or the R squared, which is the coefficient of determination. The bad news is, the standard error says model 1, the R squared says model 2, but look at how close these numbers are. You may say, oh, these are much farther apart, so I'm going with that, which says model 1. You get it? But it will be clear. You won't have to tell me which model you're using. It will be the same answer whether you're using one or the other based on how many explanatory variables there are. You're gonna get the right answer. You know, some of you may even use R squared, and some of you may use standard error, but you're still gonna get the same answers. And those would both be right if they have the same number of explanatory variables.
So it's one x.
No, if the two equations have the same amount of explanatory variables, it could have 2 explanatory variables and the other one has 2, you use standard error. Or coefficient of determination. No, I mean the number of, one model could have 1x, another model could also have 1x, you're using those. Or one model could have 2 different x's, and another model could have 2 different x's, and you're still using these because they have the same number of x's.
But they're different.
If there's different number of x's, you use the third one, adjusted. Adjusted if they have a different number of x's. If they have the same number of x's, you use one of these, different number of x's this one. I'm breaking it down to x's.
How do you know which one to use then? For the
Either one,
two.
I'll accept either one of these if they have the same number of x's. At either one of these, if they have the same number of x's. If they have a different number of x's, you gotta use the adjusted. Now, I'll make sure the last part is how to calculate the adjusted. And I have one more example too, darn it. We may have to skip a little because we want to get out early, don't we? Isn't this a holiday today? Isn't it the National Shopping Days? I can't remember. Didn't Bitcoin hit over 100,000 yesterday?
Sure, you should have hold.
For just an extra 3,000 in value is not worth it. To take the risk. I'm happy. All right, hang on, let's get to the last one. Adjusted, here it is. Adjusted coefficient determination. There's the formula. To get your adjusted R squared, you gotta take that right there. Order of operations is an important part. You gotta do this parentheses here. You gotta do the numerator, denominator, and then divide here, then multiply here, then subtract from 1 last. That's the last part. All right, where's our coefficient? Anybody take this 12? I got it on here, don't I? Let me take this, I'm gonna set this up based on that coefficient of determination. I gotta remember what the number is though. 0.89, I'm rounded, 0.89, so here we go. I'm gonna do it right here. Ready? 1 minus, look at the parentheses. 1 minus, parentheses, 1 minus 0.89. Now be careful. This is where everybody squares, but it's already squared. 0.89, r squared represents coefficient of determination, r squared. It's already squared. You just use 0.89, you don't square it. All right? Hang in there, guys. Give me a few more minutes, you guys. There. Give me a few more. Ready? N minus 1. Here we go. How many do we have there? I forgot. 1, 2, 3. So this would be 3. What is it? N minus 1? 3 minus 1. There's the numerator. Denominator. 3 minus K is how many explanatory variables? We have only one X there, not 2. 1. 3 minus 1 minus 1. There it is. That's the equation, defined adjusted. I'll show you right here. One minus, see right up here, 1 minus, parentheses, 1 minus E22, which is where this 0.89 is, times, in the numerator, 3 minus 1, divided by 3 minus 1 minus 1, equals 0.7857. Now here's what I want to do. I want to show you how all these numbers can be done automatically. You ready? We're talking about our coefficient of determination, our standard error of the estimate, and our adjusted coefficient of determination could all be done automatically. Here we go. Data. Data analysis. Go down to regression. Hang on, let me find it. Regression. Click OK. Input range. Input of your Y is going to be right here. Oh, wait, are we using labels? I forgot we're using labels. Let me get that back out of there. So do Y all the way down. There it is. Your input X, including the label. So here it is. All right, I'm going to do a new worksheet. I already did this once. I'll do it again though. Here we go. I'm going to click OK. Let's look at it. Multiple R squared. There's our coefficient of determination, 0.89. Look at what we used, 0.89. Here's the next one right here. Adjusted R squared, 0.78. Let's go back to sheet 1. Let me go down here. What was our adjusted? Right there, 0.78. Then look at our standard error. Let me open this up a little. Here's our standard error right there, 1.224. Let's go back to page 1. We calculated right there, 1.2247, blah, 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 4744871. All that work we did to get those three numbers, our standard error, our standard error of the estimate, our coefficient of determination, and our adjusted coefficient of determination can be done by using the regression data analysis. Everybody there with me?
So if on the test we put in the numbers into an Excel and ran regression, would we still get full credit because we didn't show the work?
No. Only if it says use Excel only to solve this. But I don't think I would think I would just give you this output.
That?
I would give you something like this, and I'd give you another one from Model 2, just that top box from, I'll put Model 1, Model 2, and how many explanatory variables are, and then you gotta analyze that.
Can you give another example? I know you.
Yeah, right here, I got another example ready right here.
No, I mean like out loud, like
Oh,
like if you go back to the Excel, you would say like if I ask you like that
go back one,
to the Excel.
that shell, the Excel
Excel.
spreadsheet, right here, the page, sheet 1 though, right here,
No, the second one.
this right here?
Yeah. So like an example of when we would use like standard.
When we would use what?
Because you would provide us with that, so then.
Yep,
What
R
was the question?
squared, you know what that is, right? R squared, that's the coefficient of determination. So, if I had another one there, I'd be asking you which one's a better model. See, but I don't have another one there, so that's why I'm gonna go to this instead. Here's two outputs right here. See how there's two Model 1 and Model 2? You have two different outputs there. That's what I would do on the quiz, is give you two of them, so you can compare the two. And I'm gonna say to you, now look above it, look at how many explanatory variables are on each one of those models, and I want you to tell me which numbers you're using to tell me which model's better, model 1 or model 2. Anybody want to take a shot at this? No, it's a question time. Someone, say again, before we answer a serious question. Someone take a shot at this. Which model's better, and which number should you use?
One.
You're saying one, she's saying different, you're saying one, but no one's telling me which numbers are you using?
R squared.
No.
0.748 and 0.747. Why are you using the adjusted R squared, not R squared? Why the adjusted? Because each model has different number of explanatory variables. Model 1 has 1, model 2 has 2 x's. And so you've got to use the adjusted 0.748, 0.747, and which model then is better? Model 1, because it has the higher adjusted. Do you get it? You're still, this is almost too much information. You might as well just take the quiz right now. Or quiz. It's not even a quiz, is it? Darn. How many minutes do you have?
42.
15.
42. How did I tell you how to, oh, I'm sorry, you had a question, I forgot. Go ahead. Okay, I gotta have it. Hang on, I'm gonna put it on the board. Hang on, I gotta have it in front of me. Where am I? So, 1 minus 1 minus, this is gonna be the R squared, which is the coefficient of determination. This is sample size minus number of explanatory variables, minus 1. There's that. Up here is sample size minus 1. There it is. That's all it works. Ready for the in-class?
Yep.
You want to skip it? What'd you say? Stop. This is a chance, is this our last in-class? This is a chance for people, oh, take 0? Now you're talking to me. Wait a minute, you're saying if we skip it, I can give everybody 0? No. Oh my God, let's all agree to that.
Wait, what happened?
I'm the only one raising my hand. Okay, there's 2 of us.
Wait, what?
He's saying we skip the, I gotta turn off the video on this one. See, everybody gets a 0. And I haven't drank in like 6 years, but I'll drink on that.